promise. So for everyone who's present, if you don't know what copulas are, I will tell you. And in the first half, for people who have no knowledge, prior knowledge of copulas, I'm going to try to give you an introduction with some practical examples. And in the second half, I'm going to tell you about very recent research, which I think is quite promising. So there's something for novices or people who have no prior knowledge, and there's something for people who have quite a lot of prior knowledge. And let me start to share my slides. So actually, I'll share my whole desktop and we'll go into okay, so Joan, I've now gone into presentation mode. If you see a question in the chat you think I should answer, then perhaps you can bring it to my attention. So hopefully you're now looking at my, my front page. So this is what I have in store for you. The three sections today. So I chose a topic that is different from the one I did last week. I will make a connection towards the end when I talk about copulas for time series. But in the first third, the first chapter, I'm going to go through fundamentals. And at the end of that chapter, I'm going to do some demonstrations with R so that you see that these are quite practical tools. And then chapters 2 and 3 are a bit more advanced, more recent research, which I think is interesting in certain situations. And that will mainly be after lunch in the second session. So fundamentals of copulas. Let me begin at the beginning with the definition, some basic properties, and then move into examples and estimation. So if you just need to be able to answer Jose's question about what is a copula when you meet someone and they say, what's a copula? Then I've put that on this slide, number 5, and I've put it in red. So that's the definition in red. A copula is a multivariate distribution function with standard uniform marginal distributions. So of course, a uniform random variable is a variable that takes values on 0, 1, uniformly distributed in that interval. It's the basis of random number generation, is you generate uniforms on an interval. So a multivariate distribution whose one-dimensional marginal distributions are standard uniform is a copula. Now, why a copula is interesting? Well, it all really comes from what's called Sklar's theorem, which has 2 parts. And the first part of Sklar's theorem tells you where you find copulas, which is actually everywhere in the world of distributions. And the second part tells you how you can use them in a very constructive way. So the first part says, if you have any kind of joint distribution, like a multivariate normal or a multivariate student, or something much more exotic, and it has certain marginal distributions. So this word you will have to get used to if you're new to copulas. A marginal distribution is a distribution of one of the random variables, or each of the random variables taken on their own. So we're working in dimension D. F is the joint distribution, and F1 to FD are the marginal distributions of each individual risk or risk factor or random variable. And what Sklar's theorem says is that there is a copula, there's always a copula that connects the marginal distributions together to give you the joint distribution. So you can always write a joint distribution function as a copula evaluated in a set of marginal distributions. So the copula is a linking function. Now, this is the distribution function I've written here. It's not the density. We'll come to densities later in the presentation, but this is the distribution function. The probability that the first risk is less than x1 and the second risk is less than x2, etc. And if this C was simply a product, so if the function was simply a product, what we'd be saying is that the joint distribution is a product of the marginal distributions. That would be independence. But when we take anything other than a product here, or when we find anything other than a product here, we have dependence between the risks. Now, copulas are most convenient in the world of continuous distributions. So if we're talking about a distribution which has continuous margins, normal, student, exponential, then there is a unique C. There's a unique copula that joins the margins together to make the joint distribution. So in every multivariate distribution, there's a copula. In the multivariate normal, there is a copula. In the multivariate student, there is a copula, but there is a whole universe of distributions, of d-dimensional distributions, and inside each one, there is a copula. Now, the converse explains why copulas are so helpful, because if I take a copula, any copula, and I've just told you I can find them inside other distributions, but if I take a copula and I take any collection of one-dimensional or univariate distributions, and I define F with the same formula, then I know that F is a proper multivariate distribution function, and I know that its marginal distribution functions are F1 to Fd. So this solves already a very nice problem, which is if someone comes to you and says, I have two risks, and one is, one has a log normal distribution and the other has a gamma distribution or a Pareto distribution. How can I put them together to get a joint distribution? Then the answer is you can take a copula, any copula, and you can use the converse of Sklar's theorem to put these two one-dimensional distributions together, and you'll get a joint distribution that describes their joint behavior. But of course, the question is which copula do you want to take? Because you have, in a sense, infinite choice. And so that comes down to what sort of properties do you want? What sort of dependence properties? Jose mentioned extreme dependence, for example. Do you want a copula that can model particularly extreme forms of correlation in the tail, for example? Okay, so that's the basics. Now, excuse me if I give you two mathematical facts, because if you understand these facts, then you'll find it much easier to work with copulas. And these facts are really the basis of stochastic simulation. And don't worry too much if they're new to you, but if you can understand these, then it's extremely helpful for getting to grips with copulas. And so these operations are called probability transform and quantile transform. And in fact, I used one of them last week when I made pits. I think you remember I was working in backtesting with pit or probability integral transform values. I was using the probability transform. And the idea is simply that if you have a random variable, x, with a continuous distribution, and you transform it with its own distribution, then you get a uniform. So transform x with its own distribution, f, you get a uniform. That works for continuous random variables. The quantile transform is the inverse, if you like. And that says if you start with a uniform, and you start with a distribution function f, and in fact, this time it can be any distribution, whether continuous or discrete, and you apply the inverse of f to u, then you get a variable that has the distribution f. So you use this in random number generation. For example, if you want to generate exponential random numbers, you usually start by generating uniforms, that's u, and then you take the quantile function of an exponential and you apply it to the uniforms, and that gives you a sample from an exponential. Now, don't be confused by the arrow. This is my notation for an inverse, could be a -1. In general, in order that this is always true, it should be a generalized inverse, but don't worry about that either. We take the inverse. Okay, so let's run through some basic properties. I said in Sklar's theorem that inside every f there is a copula. And if you want to get it out, if you want to extract it, then the way you do it is this. You take the distribution function f and you insert the quantile functions for each of the marginal distributions. And that allows you to isolate the form of the copula. it may not be a particularly pretty or closed form function. Sometimes it is, sometimes it isn't, but in theory, you can take it out by this operation. So that's how you can find copula functions. The next property, something that's very nice about the copula and which contrasts with correlation, is an invariance property, that if you have a random vector and it has a copula, and if you do transformations of the components of that random vector. So for example, you take exponentials. That's a strictly increasing transformation. It's not a linear transformation if you take an exponential of every variable, but it is a transformation that will not change the copula. The copula is not changed by any strictly increasing transformation. Now the correlation matrix is. The correlation matrix is only invariant if that transformation is a linear transformation. People sometimes talk about linear correlation. Correlation is a measure of linear dependence. But the copula is a non-linear object that captures dependence, and it has this property, which is very useful. So let's talk about three fundamental copulas. Copulas are about dependence, and independence is a special form of dependence. So if I was to take this function of u1 to ud, so I simply have the product of u1 times u2 times u3, if I were to put that into this formula here, I'd be saying that the joint distribution is a product of the marginal distributions, which is what we know as independence. So that's a special copula. Another special copula, is what we call the comonotonicity copula. And this is the copula that represents the strongest form of dependence you can have, the strongest form of positive dependence. If every variable was actually a deterministic and increasing function of every other variable, that's a very extreme form of dependence, because when one variable is large, the other variables are all large. When another one is small, the other ones are all small. And so this is called comonotonicity, and it has a special copula, which is actually the minimum of the arguments. So there is a convention in copulas that the comonotonicity copula gets called M, and instead of C. Usually I'm going to use C, but often the comonotonicity is called M. There is an opposite concept in 2 dimensions, which is counter-monotonicity. So if you had 2 variables which were related by a decreasing function, a deterministic and decreasing function, that's counter-monotonicity. When one is large, the other is small, and vice versa. That has a copula, which is usually called W instead of C, which is given by the maximum of u1 plus u2 minus 1 and 0. Because it is a distribution, it can't become negative, and so the maximum is taken with 0. This copula, when people first see it, they say, well, why didn't you do that for dimension D? If you do comonotonicity for dimension D, why don't you do counter-monotonicity for dimension D? As a concept, it doesn't exist in more than 2 dimensions, because if you have 3 variables and 1 and 2 are counter-monotonic and 1 and 3 are counter-monotonic, then 2 and 3 will actually be co-monotonic. You can't have 3 things which are mutually perfectly negative dependent. So, but again, don't worry too much about that. It's a small detail, and I'm going to concentrate on practical things as we go on. So let's talk about examples. And while we're talking about examples, it actually helps to talk about simulation, because we see how we can construct these models. And one of the big uses of copulas is in Monte Carlo risk models. With Monte Carlo risk models, we can choose the marginal distributions we want for our risks, and we can choose the copulas, and we can simulate them. So using the converse of Sklar's theorem. Okay, so where do you find copulas? Well, there are basically 2 possibilities. One is you use Sklar's theorem and you look inside well-known parametric distributions and you take their copulas. And so you look inside the multivariate normal and you take the copula from that, and that's the Gauss copula from the Gaussian distribution. Or you look inside the multivariate student and you take the copula out of that. And as I said, there is always an extraction operation that you can use to take the copula C out of the distribution function F using the quantiles. Such a copula may not have a simple closed form. The other possibility, there are some well-known constructions for copulas which give simpler parametric forms. So there are some explicit constructions. And the best known example is the Archimedean family, which wasn't invented by Archimedes. It's not that old. Copulas are a 20th century invention, but it relates to a property of the real numbers known as the Archimedean property in some obscure way. So these copulas are called the Archimedean Copulas. And they have more limited numbers of parameters, but they tend to be a little bit simpler. And so we'll look at a couple of those. Right, so the first possibility, implicit copulas. So you should, I think, be looking at the Gaussian or the Gauss copula. So I've written CPGA, GA for Gaussian, and P for a correlation matrix. In fact, I've chosen P because it's a capital rho as well. So the Latin P is also a Greek capital rho. And we often use rho as the Greek letter for correlation. So you can actually think of this P as a rho. It's a correlation matrix. The other things that you see here, the thin phi is the normal distribution function, the standard normal CDF that you find in statistical tables and has been known for a long time, whereas the bold phi is the joint CDF of a multivariate normal, and in particular of a multivariate normal which has dimension D, which is centered at 0, and which has covariance matrix equal to a correlation matrix. So rho is a correlation matrix, and phi rho is its CDF. So there are some special cases. If all the correlations were 0, so if this matrix, if all the correlations were 0, that's the identity matrix, then you would get independence. So the Gaussian copula contains independence as a special case when all the correlations are 0. But as all the correlation parameters go to 1, as they increase and tend to 1, you also get, as a limiting special case, comonotonicity, perfect positive dependence. And so if P equals JD, JD is the matrix that has a 1 in every position, the D by D matrix, which has a 1 in every position, that corresponds to comonotonicity. So that's the Gaussian family. The T is similar, it has a very similar construction in that you see quantile functions of a univariate T distribution, I beg your pardon. So T nu is the CDF of a standard T distribution, and nu is its degree of freedom, whereas the bold T is the joint CDF of a multivariate student distribution, which has a correlation matrix of rho and a degree of freedom nu. So you probably recall that the T distribution has a degree of freedom. That's also true of the multivariate T distribution. You may not have encountered this distribution, but it's like a D-dimensional generalization of student. It also has a degree of freedom, nu, and as that degree of freedom, nu, tends to infinity, you get closer and closer to normality in the limit. And so this one I call CT, and it has two objects, which are its parameters, the degree of freedom nu and the correlation matrix rho. So you can think, if you like, of this Gaussian copula as a limit as nu goes to infinity. An interesting thing, however, when P is the identity matrix, so if we take this case that I talked about here, where P is the identity matrix, in this case, you don't get independence, because whenever the degree of freedom is finite, this CDF does not factorize into a product. And so, in fact, even with zero correlation, the T copula is not a model for independence. And people find this counterintuitive. How can it be that zero correlation is still dependence? That's because correlation is a very much weaker concept than copulas. So zero correlation does not mean independence. And this is a very good counterexample. We can set up a T copula to have zero correlation, but it will still have dependence, particularly in the extreme values. Let me move on to two Archimedeans. Now, these are a little bit simpler to look at. If I just jump back quickly, you can't really write these in much simpler forms, these two here. To actually write down the joint distribution function of these copulas, you find yourself writing integrals over a density. So in contrast, the Archimedean copulas consist of simple mathematical functions, like exponential, like logarithm. So Gumbel's copula, GU for Gumbel, it has a single parameter theta. It doesn't have a whole matrix of correlations. It has a single parameter theta, and theta must be greater or equal to 1. If it is 1, you get independence as a special case. And as theta gets larger, you converge to perfect positive dependence or comonotonicity. So you can model positive dependence all the way from independence through to comonotonicity, but in quite a restricted way, because when we only have one parameter theta, we have what's called an exchangeable model. So every pair, in d dimensions, every pair has the same level of dependence. So we can't have one pair more dependent than another with the Gumbel copula. Every pair must have the same level of dependence. And that's also true of Clayton. It's another so-called exchangeable Archimedean copula, and it has a parameter theta. Theta must be positive. As theta goes to 0, you go to independence. As theta goes to infinity, you go towards comonotonicity. And that has an even simpler functional form. And it always has the property that it is a multivariate distribution function in its own right, and the marginal distributions are always uniform, as we'll see in the simulations that we do. There are other examples. So Frank's copula, Joe's copula are quite well known, and quite a few other examples of Archimedean copulas. But those four will do to begin with. So it is helpful to simulate these distributions. And in fact, that's one of the things we do with copulas. I've already said, we use them in Monte Carlo risk analyses. We use them in stress tests. We want to generate data that have certain copulas. So whenever a new copula is proposed, it's important to know how to generate points from that copula. So I'm going to start with the Gaussian copula. How would you get points from it? And we'll do this to make it clear that it's not particularly complicated. Well, it's two steps. You generate a Gaussian random vector centered at 0 and with some correlation matrix. So you generate X, and then you use probability transformation on every component. So you take the first component and you transform it with a standard normal CDF, and that makes it uniform. And you do the same thing to component D. Transform it with its own standard normal CDF, and it makes it uniform. Just as a note, generation of the multivariate normal. In every statistical software, we have the univariate normal. In some software, we have the multivariate normal, but it's usually accomplished with the following 3 steps. You can generate independent normals. You can take the correlation matrix and you can decompose it using the Cholesky decomposition into a lower triangular matrix and its transpose. And then you can multiply the vector of independent normals with the Cholesky matrix, and you get a vector X, which has this normal distribution. We'll do that very quickly in R shortly. So everything I say here, we will do briefly, but concretely using R in the next part. Now, my 4 copulas, I've generated points from them. So I've only mentioned here how to do the Gaussian copula. The T copula is equally straightforward. The copulas of Gumbel and Clayton, which are in the top right and the top left, that's a little bit more involved, how you generate points from them. As I said in last week's course, I have a textbook and that has all the algorithms. But at this point, they're available in software, as we'll see. So what you see here is 4 point clouds, and they are displayed on the unit square, so 0, 1 to 0, 1. And if I were to draw a histogram or make a histogram of the first component of any of these pictures, it would be uniform. It would be absolutely uniform. And if I were to do the same thing for the second component, x2, it would also be uniform. So these are points from 4 distributions which have uniform margins. And the choice of parameters will look a little bit arbitrary. For the Gauss, I took rho is 0.7. For the Gumbel, I took theta is 2. For the Clayton, I took theta is 2.2. And for the T has 2 parameters. It has a correlation, which I took to be 0.71, and it has a degree of freedom, which I took to be 4. And there is a reason for this eclectic set of parameters, which is coming up. But what I want you to observe here is that the point clouds look a bit different. I think you particularly see that the Clayton looks like it has an arrowhead in the bottom left, and the Gumbel looks like it has a point in the upper right. And the T, maybe you can see this, maybe the T looks a little bit more pointed in the top right and the bottom left than the Gumbel. They have slightly different character, the Gaussian and the T. And the Gumbel and the Clayton have rather different character. Now, let me move on to the next idea, and then you'll see why I chose these parameters. The converse of Sklar's theorem is used all the time to build models with desired margins. So if we have a copula C, and if we take any collection of univariate distribution functions, and if we put the F's together using the C, and we call that F, then F is a multivariate distribution with margins F1 to Fd. And we often refer to F as a meta distribution with the dependent structure represented by C and with whatever margins we choose to use. So for example, if C is a Gaussian copula, we get what's often called, or sometimes called, a meta-Gaussian distribution. If C is a T copula, it's a meta-T distribution. Now, why did I say dependent structure represented by C? This is an interpretation that I've now put on a copula, and which I perhaps should have mentioned earlier. Because the copula describes how the margins are put together to make the joint distribution, you can think of it as describing the dependent structure. And it helps that it is an invariant representation of the dependence under increasing transformations, in contrast to a correlation matrix. So a correlation matrix is not the dependent structure, but a copula is a good representation of the dependence within a distribution. So, for example, I could put distributions together with a Gaussian copula, and I could get data which have any kind of marginal behavior I want, exponential, Pareto, etc., log normal, anything I want, but their dependence would be described by whatever copula I use, the Gaussian copula. The same with the T copula. The dependence of the points is governed by the T copula. The marginal behavior can be anything you want. And how do you actually generate these samples which have any margin? Well, if we can sample from a copula C, then it's easy to sample from the distribution F. We generate a vector from C, as we basically did in one of these pictures here. And then for each of the components, we apply the desired quantile function. Anything we want, any quantile function we want, will change the uniforms into that distribution. Now here, I've done it with normal margins. So in fact, the quantile functions F1 and F2 are normal quantile functions. And I get 4 distributions. And only one of them is a bivariate normal. The first one here, which says Gaussian, these points are actually from a bivariate normal. They have the Gaussian copula and they have standard normal marginal distributions for x1 and x2. But the other 3 are data from a distribution which has the property that the margins are normal. So x1 and x2 are normal in every single picture here, but the copulas are different, and therefore the distributions are different. So the Gumbel one, you see that the points in the upper right are very close to the line y equals x. We often say that this one has upper tail dependence. The most extreme positive values are very dependent, whereas in contrast, the Clayton has lower tail dependence. The most extreme values down here are particularly dependent. They're very close to the line. The T copula has more points here than the Gauss copula does, and also more points here than the Gauss copula does. In fact, the T copula, and the degree of freedom is 4, so T4, it has tail dependence in both the bottom tail and the top tail. Tail dependence is a concept I'm not proposing to define formally or go into in a formal way, but there is a formal concept of tail dependence, and to give you the punchline, the T copula has it, but the Gaussian copula doesn't. So the T copula has a tendency to give you joint extreme values. The Gaussian copula doesn't really. Now, back to those strange strange parameter choices. Why did I take the parameters that I took? I did that so that in every case, I would get a distribution where the correlation, the ordinary Pearson linear correlation, would be 70% or thereabouts. So here I'm using rho to signify linear correlation. So in every one of these models, correlation is 70%. So when Jose said that correlation isn't enough, this is the reason. I have 4 distributions and they all have the same correlation, 70%. Moreover, they all have the same marginal distributions, normal, but they're very different distributions, and they're going to give you in particular different dependence in the extreme values. Okay, we will repeat that in R, and we'll add a few other details to it very shortly. But what I want to do is I want to cover estimation first, and then we can have a look at all of that in R. So a copula is a distribution function, and it can be fitted to data. So if you have some data, you can estimate a copula. So this is the setup here that we're talking about. Let's suppose that we have data vectors, n of them. Okay, and we're assuming that they come from a common distribution, F. And we assume that F, let's assume for simplicity that it has continuous marginal distributions, F1 to Fd, which means that by the theorem of Sklar, there is a unique copula C. And we will further assume that C belongs to a parametric family. So something like Gauss or T or Clayton or Gumbel, or many, many others. And if we want to estimate C, so if we really want to understand the dependence structure, then we're first going to need to estimate all of the marginal distributions. In a sense, in copula inference, we're most interested in finding out about the dependence structure. And in that sense, the marginal distributions are nuisance parameters often, but it depends. There may be some applications where both are equally important, where you want to know what are the best distributions for each of my risk factors and what's the best copula to describe their overall dependence. And so there are two main approaches that people use, which can be summarized as parametric inference for margins or non-parametric inference for margins. And so the first one, the parametric function, Harry Joe, who has a very well-known book about copulas, in fact, 2 books about copulas, he proposed that in a first step, we estimate these distributions with parametric distributions. So we look at them really carefully and we try to find the best model for the first risk, whatever that is, normals, students, hyperbolics, generalized hyperbolics, whatever. There are many distributions, but for every risk, we can choose a different one. And then when we've estimated these distributions, after that, we estimate the copula. I'll come to that in a minute. Or Christian Genet and his collaborators in Quebec, they proposed pseudo maximum likelihood copula inference, which is we estimate the marginal distributions empirically, non-parametrically, using the empirical distribution function. So in this case, the jth margin, so fj, is estimated by taking the empirical distribution function. And the only thing that, if you know the empirical distribution, the one thing you might notice is that the division here is by n+1 instead of n. That's done so that the points we obtain are strictly within the interval 0, 1. But for large n, it's not, it's only a detail really. And so you first estimate the margins, and then in stage 2, you estimate the copula. So having estimated the margins, you transform the data with the estimated margins. So for the first components, you transform them with f1 hat. For the dth component, you transform them with d hat. You do that for all of your observations, I is 1 to n, and you get a pseudo sample. It's a pseudo sample because you're not sampling it directly, you're sampling from f. But by this method, you're creating an artificial or a pseudo sample from C. So UI hat is our reconstructed sample from the copula. And when we have that, we can fit the copula by maximum likelihood. So the copula is a distribution function. For the first time, let us look at the density. From the copula, we can compute the density. Sometimes that has a much simpler form than the copula itself. For example, for the Gauss copula, the density arguably has a simpler form than the copula. And then we can maximize the log likelihood of the data, or the likelihood of the data. So we can form the log likelihood, we can maximize it with respect to the copula parameters, and we can choose the best fitting copula. I've assumed here that all of my vector observations are independent. There are a couple of small issues with that. To begin with, we can apply this method to data which have serial dependence because they come from time series. And so it doesn't tend to be a problem if we have enough data in terms of getting point estimates. The other issue is that in forming a pseudo sample, even if the original data were independent, when you form a pseudo sample, you actually introduce a little bit of dependence through the common marginal estimates. So for simplicity, we'll assume independence, and most software does that. Okay, one final idea before I go through these ideas one more time, but in practice, and that is rank correlation. So there is an alternative to maximum likelihood, and that is the idea that we estimate copula parameters using a rank correlation. Now, the first immediate question is, well, why rank correlation? You may have heard of rank correlation if you've done experimental statistics. You may have heard of things like Spearman's rank correlation or even Kendall's rank correlation. They're quite widely used in empirical statistics or applied statistics, but you might wonder why for copulas? Why not ordinary correlation? Now, ordinary correlation gets called two other things. It sometimes gets called Pearson correlation after Carl Pearson, the statistician who worked on it, or it gets called linear correlation because it's a measure of the linear dependence. Well, the reason we don't use linear correlation to estimate copulas is that the correlation of a bivariate distribution depends on both the copula and the marginal distributions. So if we were to compute the correlation, it would depend both on C and on F1 and F2, if we think of a bivariate distribution. So it is something that depends on the whole distribution and not just the copula. Moreover, it's not necessarily invariant under one-to-one, strictly increasing transformations of the margin. That is a property that the copula has that the correlation matrix doesn't, which can be convenient for estimation. Another important reason we don't use linear correlation is that the range of attainable correlations is not equal to -1, 1. So what do I mean by that? It's probably commonly thought that irrespective of the marginal distributions F1 and F2 of two risks, that you ought to be able to find models that have any correlation between -1 and 1. So whatever you want, -70%, +90%. It might be thought that there should be a model that has any correlation you want for given marginal distributions. That's not actually true. There is a range of attainable correlations. There's a set of values you can get when you fix the margins. And it doesn't have to be equal to -1, 1. And in fact, it can often be quite limited. That once you've chosen marginal distributions, if they're quite different, that you have a very limited range of correlations that you could actually attain in a joint model. Now, rank correlations don't have those three problems. Rank correlations depend only on the copula. They have nothing to do with the marginal distributions. I'm going to say what they are next. So if you're thinking, what is a rank correlation? That's coming up. But just to tell you why I'm going to look at them, they only depend on the copula. So that means they inherit the property of invariance. I should really have said strictly one-to-one increasing transformations. So they're invariant under strictly increasing transformations. And importantly, you can attain any value between -1 and 1. Once you fix the margins, by appropriate choice of a copula, you can get any rank correlation between -1 and 1. Why is this so important? Well, in the world of Monte Carlo scenario generation, rank correlations are very commonly used. I first learned about this at least 20 years ago when I looked at some software, which you can still buy. It's called At Risk. It's quite popular with insurance companies. And from my first talk, you might remember that I'm actually a professor of actuarial science, so I often work with actuaries. A lot of them know this At Risk software. You might have seen it at a bank. But it's a software where you can generate data with any distributions you want and with arbitrary correlation structures, but you must specify the correlations using rank correlations. Otherwise, the method does not make sense. And so if you want to make a model which has whatever distributions you want for the margins, So you might want a normal and a hyperbolic and an F distribution, an operator distribution, or a Cauchy, anything you like for the different risks. But you want to specify their correlation structure, then you do it with the rank correlations, not with the Pearson correlations. So there are two varieties of rank correlation. There is Spearman's rho and there's Kendall's tau. And I'll start with Spearman's rho, but today I'm going to spend more time with Kendall's tau. So Spearman's rank correlation, in fact, I'll call it rho S. If you have two variables, then Spearman's rank correlation is actually Pearson's correlation of the probability transformed risks. So rho here is Pearson's correlation or ordinary correlation. And if I were to apply that to not x1 but an x2, but f1x1 and f2x2, then I'd get Spearman's correlation. And of course, this being the probability integral transform, that gives you a uniform variable. And so what you're actually really doing is you're calculating the correlation of the copula. The copula is precisely the distribution function of f1x1 and f2x2. Didn't make that point earlier, but the copula is actually the distribution function of the probability transformed variables. So Spearman's rho is the linear correlation of the copula, and therefore can be calculated from the copula. In the most general case, you have to do an integral, but this can be a very easy integral for some copulas. But the important thing is this formula, I highlighted, this formula here has nothing to do with F1 and F2. They've disappeared. Rho S depends only on C. F1 and F2 have disappeared. They don't matter for Spearman's correlation. Now Kendall. Kendall is slightly different to define. So the idea here is, suppose we take an independent copy, x1 star, x2 star, of x1, x2. So x1, x2 has some distribution. And then we take another pair that has the same distribution, but it's an independent pair. Kendall's rank correlation, which is sometimes called Kendall's tau, is calculated using this formula here that I've just highlighted. It's the difference in two probabilities. But if I just write down the blue formula, this is a little bit opaque. So what am I doing? I'm taking x1 minus x1 starred. I'm multiplying by x2 minus x2 starred, and I'm saying what's the probability that that's positive? And then I'm taking away the probability that it's negative. Well, this probability is the probability of concordance. And this probability is the probability of discordance. So what I'm really doing is I'm subtracting the probability that two random points from the distribution are discordant from the probability that two random points from the distribution are concordant. Let me show you a picture before I go back to that. Discordant and concordant. This is quite a nice way of looking at it. But if I pick x1, x2, let's suppose I pick an x1, x2, and let's suppose I pick that one. Every point here is a point from a distribution. So every point here comes from a distribution, and I fix one of them. So the sets of points which are concordant with x1, x2 are either in the top gray square or the bottom gray square. So every point here is a concordant point with x1, x2. It's concordant because if you go, if the x coordinate is bigger, the y coordinate is bigger. That's all it is. If the x coordinate is bigger, then the y coordinate is bigger. Or if the x coordinate is smaller, then the y coordinate is smaller. But for these 3 points here, they are discordant. They're discordant because in this case, although the y coordinate is bigger, the x coordinate is smaller. So in this distribution, for that point there, most of the points are concordant and 3 of the points are discordant. And in general, Kendall's correlation is the probability that 2 points are concordant minus the probability that 2 points are discordant. And because points are either concordant or discordant, you can actually write it as twice the probability the points are, twice the probability of concordance minus 1, because this probability is just 1 minus that probability. Why have I labored this point about concordance? I'm going to need those numbers after lunch when I talk about attainable correlations. So I wanted to say a little bit about concordance, and I'll come back to that as well. Now, this looks abstract, and in fact, once again, tau can be calculated directly from the copula. So if you take the copula function and you integrate with respect to the copula density, multiply by 4, subtract 1, that gives you Kendall's tau. And once again, it's only a function of the copula. F1 and F2, whatever marginal distributions these points have, that's unimportant in computing Kendall's rank correlation. So those are rank correlations. And I just have 2 more things I want to do, and then I'm going to move into a more practical part. So first, to say that for all of the copulas I've shown you, there are formulas for rank correlations. And in general, for Kendall's rank correlation, there are more available closed form formulas than for Spearman's correlation. So Kendall is a bit more useful in the world of copulas than Spearman. So for example, suppose you had the Gaussian copula. If x1 and x2 have the Gaussian copula, that has a single parameter rho in the bivariate case. In the bivariate case, there is a single correlation parameter rho. Then the Kendall correlation is 2 over pi arcsine rho, and the Spearman correlation is 6 over pi arcsine rho over 2. Now, what's quite nice is that the first formula is also true of the T copula. So if the 2 risks had the T copula instead of the Gauss copula, in fact, this formula remains true for the T copula. The degree of freedom doesn't enter. So the degree of freedom in the T copula has no influence on the Kendall rank correlation. And you may have heard of the class of elliptical distributions. Gaussian and student are elliptical distributions. So they are distributions which have elliptical contours. So if the density, if you look at where is the density equally, where is the distribution equally dense, the locus of those points is an ellipse, or the loci of those points is an ellipse. The contours of the density are ellipses. That's true of the Gaussian distribution. The normal distribution is true of the multivariate student T, but there are many others. And in this first formula is true for all of them. There are explicit formulas in terms of theta for many Archimedean copulas. So in fact, we have both Spearman's rho and Kendall's tau for the Archimedeans, but in general, the Kendall's tau tends to be more widely available. Now, why is this nice? Well, one reason is that it permits an alternative way of estimating, method of moments, because suppose I'm trying to estimate the Gauss copula. Let's take, for example, I'm trying to estimate the Gauss copula. If I knew the Kendall correlation, then I could invert the formula to find rho. Okay, if I knew tau, I could invert this formula to find rho. But I can estimate tau. I can estimate tau because each of these measures here, these are theoretical measures for random variables, but each one has a standard estimator that is very simple to carry out and which is widely used in experimental statistics. So each of these is easy to estimate from data. So if I have some data, let's say I have n pairs. So here I have n pairs. The usual way of estimating Kendall's tau is to compute this quantity here. The reason these measures are called rank correlation is that you only need to know the ranks of the data. You don't actually need to know what are the exact values. You just need to know the ordering of each component. And so a formula can be written down that only involves the ranks of the data. And in the case of Kendall's tau, that can be further simplified so that you just need to know certain signs, can be computed from the knowledge of certain signs. I won't go into that. In Spearman's correlation, you see more explicitly that it's calculated from ranks. So what are the ranks of a sample? If I have a sample of n data, the ranks just tell you the ordering. So what if the rank is 1, it means it's the biggest, or usually the smallest. So rank 1 is the smallest, rank 2 is the second smallest, and rank n is the biggest. So it just tells you the ordering in the sample. So you can take the data, and all you need to know in each sample, you have the sample for x1, you have the sample for x2. All you need to know is the ordering of the points within those samples. So this just means rank xi1, it just means the ranking of the ith observation of the first variable within the sample for the first variable. Is it the smallest? Is it the biggest? Is it in the middle somewhere? So that gives a method of estimation, which is an alternative to maximum likelihood. Now, I'm going to come out of Acrobat and I'm going to go into R. So hopefully what you're seeing here is my R console. So I wonder if I should make that just a touch bigger. Okay, so hopefully this is legible. Now, I'm going to show it in a slightly different way today. If you're in my backtesting class, I did this slightly differently. But as before, you have a R markdown script. So you have this file. What you see here, you have it. And you can knit it. It's probably going to be quicker than the one that I did for backtesting, which had lots of simulations, slow simulations. So if you knit it, what you will get is what you see in the viewer. So you'll see copula course. And so let me just say a little bit about what I'm doing here. I'm using 8 libraries. The first 6 of these you'll find on CRAN, which is the comprehensive R repository, where you find R itself. So 6 of them are on CRAN. 2 of them, which I'll use this afternoon, are on GitHub, and I'm responsible for them. Kendall signature, TS Copula. So it's organized into the 3 chapters. So I'm going to go through the fundamentals of copulas and just run over some of those concepts, because what I'm particularly keen is that for those of you who know nothing, that at least this morning, you come away with some sense of what the copulas are. And you can answer that question, what's a copula? Okay, so let me take that away. So what I'm going to do now is I'm going to generate points from the Gaussian copula. So lines 36 to 38, if I execute those, so you'll see that that's being echoed in the bottom corner here. If you look down here, I'm running this line by line. Z here, if I look at Z, that's perhaps not the best way of doing it. Yeah, so Z is a matrix with 2 rows and 2,000 columns, and it contains independent normals. So Z1 and Z2 are independent normals. If you look at if you look in the viewer screen, we first generate 2 uncorrelated normals. Now, how do you get correlated normals? Well, let's take the correlation matrix. Let's take the correlation matrix, which looks like this. So the correlation is 70% between the 2 variables. And I've constructed it from a lower triangular, matrix A. So A is lower triangular, and TA is the transpose, that's upper triangular. And this matrix A is the Cholesky, sometimes called the Cholesky factor. And so if I take A and I multiply it into Z, you might wonder, what are these percentages and stars? In R, if you're new to R, when you multiply matrices, then you have to wrap them in percentages so that the R knows that you should use matrix multiplication. And then I get x1, x2, and then I get the copula. So, then I get the bivariate normal distribution. So x1 and x2 have a bivariate normal distribution. So I've got to this point here. I've generated a bivariate normal. But what I'm going to do now is turn it into the copula. So to generate points from the copula, you use the pit transform. So this here is the pit transform. I take U1, perhaps I'll show it down here. I take U1 and I transform it with its own distribution. And I take U2 and I transform it with its own distribution. And then what I get is points on the unit square. To show it's a square, I should really do that. It should be a square, perhaps like that. And these are points from the Gauss copula. All I've done is I've taken points x1, x2 from a bivariate normal, and then I've transformed them with phi, their own CDF, and that way I get points which are uniform. We could check they're uniform, or crudely check. So if I was to do the histogram of U1, I get something which looks pretty uniform. Same with U2, if I was to do the histogram of U2. So they look pretty uniform. They are indeed from a distribution which has uniform margins. Right, let's go back. So we've had a look at points from the normal distribution, points from the Gauss copula. I mentioned comonotonicity and countermonotonicity. As the correlation goes to 1, these points will get closer and closer to the diagonal. So if I were to repeat this with rho is 0.9, rho is 0.95, they would get closer to the diagonal. And so in fact, the comonotonicity copula is actually the copula of points constructed in the following way. I take a uniform, I'm going to set out a plot, but what I do is I plot U against itself. So what I've done here is I've plotted, beg your pardon, I've plotted components U1, U2. I've just plotted U against itself where U is uniform, because the comonotonicity copula is the distribution of the random vector consisting of a uniform U and a second a uniform U in both components. Whereas the countermonotonicity copula is, oops, we have to do the countermonotonicity copula. I think that disappeared, did it? Yeah, it disappeared. I wanted to do that. That's the countermonotonicity copula. That is perfect negative dependence. The points are all on this line here. Let's make it more square. Points are all on this. Oh, too small. It's a bit better. Maybe that like that. The points all go from 0, 1 to 1, 0, and these are special cases of this Gaussian copula here, either as the correlation goes to 1 or as the correlation goes to -1. As it goes to -1, the points line up on this diagonal. Right, that's comonotonicity. Now, how can you generate points from copulas? You don't have to write your own code to do this. In the copula library, I'm going to set up, well, first of all, I'm going to ask for 1,000 points. So I want 1,000 points. I'm going to, don't worry about those warnings. I'm going to choose those copula parameters that I mentioned earlier. So for the 4 copulas, I'm going to recreate the example that I had in my slides. And what I do is I use commands here in the copula library. So for example, normal copula. If I look at normal copula, This belongs to the copula library. It's a construction function for one of the elliptical copulas. It happens to be the normal copula. So I construct a normal copula, NC, which has the parameter theta n. So I do that one. I construct a Gumbel copula, which has the parameter theta g, a Clayton copula, and a T copula with parameter 4. And you'll see that I've just used the default value there. I could state that explicitly. Maybe it's better to put that in explicitly. The degree of freedom is 4, so the new parameter. So I construct it. And then to generate points, there is a generic function R copula. So this generates a random sample. You can see here if I do R copula. This is random number generation for copula functions. So I can generate samples. So I'll just show you now, pick up the speed a little bit. I'm going to show you the 4 plots laid out in a nice way, I hope. I'll have to make it a bit bigger. Let's make it like that. So those are the ones I made earlier. You have Gauss, Gumbel, Clayton, and T4. You have 1,000 points, and I've generated them live. Now the idea of meta distributions, so let's just show you where I've got to. We've generated these points. We're now going to do meta distributions. We're going to combine all of the copulas with normal marginal distributions. And we're going to get 4 distributions that all have a correlation that's very close to 70%. But they're different distributions. So in R, what I do is I take the copula data and I use the quantile function of normal. You might be wondering, what's Q norm? Q norm is the quantile function of normal, whereas P norm is the distribution function. So you look distribution function, quantile function there in R, as well as the density, incidentally. And R norm is random number generation. So I've transformed them to normal. The next command is just to get an appropriate scale for the plots. And then we draw the 4 plots. And so you see that you have points from these plots. The correlation of any one of these should be pretty close to, I haven't tried this, so hopefully it is. Yeah, it should be pretty close to 70%. So for example, if I take the Clayton copula, what do I get? I get 0.68. It's a little bit on the low side, but I only have 1,000 points. And these models have been created so that the true theoretical correlation is extremely close to 70%. Now, I don't have to choose a normal margin. Of course, I could take the copulas and I could take a different margin. So in the next set of code, I'm going to use QExp. So what I'm doing here is I'm taking the normal copula data, but I'm making it exponential. And I'm going to do the same thing for the other 4. Line 138 just finds an appropriate scale so that the plots look nice. But here we go. Now I've put them on an exponential distribution. So now I have a model which has a Gauss copula and standard exponential margins. Might have a use in credit risk modeling, for example. Same thing for a Gumbel copula with exponential margins. You notice that you have more joint extreme values here with the Gumbel than you do with the Gauss or with the Clayton. The T4 also has quite a few joint extreme values. So that's generation. What about estimation? So where have I got to? We have looked at the generation. So we've looked at the normal margins, and then we've done one with exponential margins. We're now going to fit the copulas by maximum likelihood. So I'm going to reconstruct these pictures. I'm going to take some data on the it's a little bit old, this data, but you'll get the idea. So it's not up to date by any means. I take the S&P 500 index. I've taken the UK FTSE index. These are the actual index values. I've calculated returns. So I've calculated actually log returns. This function here, returns, is in a package called QRM tools, computing returns like log returns and simple returns or basic differences for different kinds of risk factors. I then merge the two and I plot. And that's where you see, I'm just going to restore the plot to see if I can put this back to. Yeah, I put the plot back to the full window. There are some zeros caused by market close days, holidays in the US, holidays in the UK. So I do a little bit of data cleaning. So this is not important. I'm removing some zeros. And what I'm going to do is I'm going to change the, I'm going to look at returns over a weekly interval rather than, it could be monthly, but I'm going to change to weekly. So these are daily. These are daily time series during the financial crisis, a little bit before, a little bit after. It's very easy when you work with return data in R to use some tools to change the time horizon. So in fact, this time I'm looking at weekly returns. So x.w, these are weekly returns. So it goes up 1 week, goes down another week on the S&P 500 and FTSE. And now my question is, of the 4 copula families, which is the best for these data? Which is the best for these data? So I'm going to use the method of pseudo likelihood inference for copulas. That is, I'm going to estimate the marginal distributions non-parametrically with the empirical distribution function. And there is a function POBS in the copula library that does this. So POBS stands for pseudo observations. POBS for pseudo observations. So you'll see here that what I do is I take the weekly data and I calculate the POBS. Don't worry about the as matrix, that just puts it into the right form. So I calculate I apply the probability integral transform, and then I get this. So these are the data. Incidentally, if we look at the dimension, there are 523 points here. So there are 523 points, two-dimensional, and you see the pattern of points. And so the question is, if I was to pick one of my 4 copulas for these data, which one fits best? And so that you use the function fit copula. The syntax is that you use fit copula, you take the name of the copula you want, or the function. So what does normal copula do? So normal copula with an open and a closed bracket, all that does is it sets up a normal copula of dimension 2, and you fit that thing to the data, and you get a fit. And I do the T, forget the warning, not important here. We fit the Clayton, we fit the Gumbel, and we now have 4 models fitted. And if I arrange them in order of log likelihood, so what I've done here is I've sorted them into decreasing order of log likelihood. So which one gives the highest value of the log likelihood? The answer is the T copula. So it gives a log likelihood of 302. It has 1 extra parameter because it has a degree of freedom. But even considering that, it's much better than the Gauss copula, which is much, much better than the, I beg your pardon, that's the Gumbel, isn't it? Yeah, that's the Gumbel. It's better than the Gumbel copula, which has 1 parameter, which is much better than the normal copula, which is much, much better than the Clayton copula. You might think, well, why is the Gumbel copula quite good? Does look like there could be a little bit of asymmetry where there's more tail dependence in the top right than in the bottom left, but there is enough that the T copula is significantly better than the Gumbel copula. And the T copula has tail dependence in both corners. So the T copula works best in this case. The next thing to say is that there would be an alternative way of estimating the T copula. Let's have a look and see what we've done. So this is the results of fitting the T copula. So each one of these things will have some results. You can see here, if I type in the name, you get the results. So let's have a look again at the T. So what it says, it's a fit based on maximum pseudo likelihood, 523 observations. The parameters are that the rho is estimated to be 0.8, and the degree of freedom is estimated to be 2.7, let's say. And the maximized log likelihood is 302.5, and it's been found by numerical means, and the optimization has converged. Now, there is an alternative way of estimating this parameter just using rank correlation. So if I were to take the weekly data and I were to compute the correlation using Kendall's method, that will give me tau. So let's have a little look at tau. So that's an estimate of Kendall's tau between the FTSE and the Spearman 500. The probability of concordance minus the probability of discordance. Then I do a little transformation. I take the sine pi times tau divided by 2, and I get the value 0.8. And that should be pretty close to this value here, because these are two alternative methods of estimating rho. That's the maximum likelihood. This is the method of estimating by using Kendall's tau. Because what I've done is I've used the formula I showed you earlier for Kendall's tau for a normal copula or a T copula, or indeed any elliptical copula. The only problem is that it doesn't give you a method of estimating the degree of freedom. So it tends to be used in higher dimensions for speed, where you can estimate the correlation parameters using the Kendall's tau method, and then you have a single degree of freedom parameter which you can estimate using maximum likelihood. That's a kind of hybrid method that's commonly used. So hopefully that gives you a sense of what I've covered in the first part. I'm going to go back to the slides now. So the final thing I did there was I showed you the use of this formula. I inverted it. I got tau, and then to get rho, I basically multiplied by pi, divided by 2, and took the sine. That's what I did. You can see that here. Multiplied by pi, divided by 2, and took the sine. And I got a number which is an alternative way of estimating the correlation parameter. Obviously, it would work for it works very well for the Gauss copula because it has no extra parameters. Right. We are at 11:44. We are not quite halfway through the course. And let me just give you a little idea of what I'll do after lunch and then maybe take questions. We did start 5 minutes early. So I'm next going to talk about more about Kendall correlations, because for choosing copula models in high dimensional situations, there are some interesting questions about how to use Kendall correlations and what are valid values for Kendall correlations. So I'm going to talk about the problem of attainability for Kendall correlations. I'll probably spend, in the afternoon, I'll spend a bit of time on that, and then I will want to go on to copulas for time series. So if you have time series data, can you use copulas? For a long time, people didn't really use copulas for time series. For example, could you do Garch modeling with a copula instead of a Garch model? My belief is that you can, as an alternative. You can actually build volatility models with copulas. So I'm going to give you some insight into that. But immediately after lunch, we're going to look at this situation. So we're doing a risk analysis, or we're doing a stress test, and we want to generate scenarios from a model with prescribed rank correlations. We don't use ordinary correlation. We don't use linear correlation because it's not a good idea. It also depends on the marginal distributions, and we want to separate the problem of choosing our margins and choosing our copula. We want to take any margins we please, and then we want to pick a copula to match rank correlations. But in truth, if we're doing a stress test, we may have very limited, or we may not have any data on some of our pairs. And I've come across it quite often in enterprise risk management that experts are being asked to give their views on what the correlation should be. So sometimes we want to incorporate expert knowledge. And I'm going to look at how one can do that, because you can't just pick any numbers. They have to be consistent, or you can create systems that make no logical sense. That's what I call unattainable. And I'm going to take an example with some cryptocurrencies where I had some data. Bitcoin, cryptocurrencies, Bitcoin, it's kind of the flavor of our times. I know you've got a course on it, so I just took this as for fun, really, as an example. And we're going to suppose that we have data on the first three. In reality, we have data on all of them. But suppose we have data on the first three, and we just have an expert opinion on the correlation with Ripple, Bitcoin and Ripple. We're going to look at how we can determine correlations when we don't have much data. And this relates to a recent paper that I've been working on, which you can find online, for determining the attainability of Kendall correlations and for completing missing values. So we'll do some of that, and then we'll go into time series, for financial time series, using copulas in that context. So that will be new material. I don't think many people will have seen this because it's just developed in the last couple of years, but it could be interesting. So Joan, I'm going to pause for breath, and I can take some questions now on what I've talked about in this first session.
Okay, thank you very much, Professor McNeil. I will read some of the questions we have in the chat, but now at this moment, people can